Hi everyone, welcome to CS 188 Section 2, Worksheet Solutions. So in this first problem, we're going to talk about search and heuristics. So if you haven't read the problem, please pause the video, read the problem, and then I'll begin talking about number 1. Okay, so in this problem, let's see the first question. If the grid is m by n, what is the size of the state space? So we should assume that we can reach all configurations of the start state. So let's go through this paragraph and see what relevant information we need to keep track of. So the agent is directional and can face some direction D. And D can take on 4 values, north, south, east, or west. So with a single action, the agent can either move forward or at an adjustable velocity V. So you can see we're going to have some velocity V, so we'll probably need to keep track of that. So the actions are turn left or right, and we also can go faster or slower. Now we can increment the velocity by 1. So that's kind of a relevant piece of information. And we can slow by 1. Now, let's see. So our velocity v is bounded below by 0 and is bounded above by Vmax. Okay, so now with this, and we also know that the agent exists at some position, some coordinate. So with that, we can make the state space. So we know that the agent has to be somewhere, so we're going to keep track of position. We also know the agent has a direction, so we can call that dir for direction. And we also know that the agent has a velocity, so I'll call that vel. Okay, so now what's the size of the state space? So what we do is we're going to go through each of the components of the state and determine how big it is. So for position, the grid is m by n, so we can be in m by n positions. For direction, we can either be north, south, east, or west, so that's 4. Now for velocity, so we can be at velocity 0, because that's written right there, and we can go all the way up to Vmax. So that means, and we do increments by 1, so that means we can take on Vmax plus 1 values of velocity. So our total state space size is going to be the multiplication of all of these. Mn times 4 times Vmax plus 1. Okay, so now question 2. Is the Manhattan distance from the agent's location to the exit's location admissible? Why or why not? So in general, let's try to break this heuristic, because if we can break it, then it's not admissible. So let's consider a very long hallway. And let's just say that the agent, which I'll draw as Pac-Man, starts there, and the goal is to get to this star. And let's say the hallway is of length m. So what would Manhattan distance return? Manhattan distance would return h equals m. However, we know Pac-Man can increase, or the agent can increase their speed to go more than 1 square per turn. So in general, Pac-Man could get there in less than m. Because if Vmax is greater than 1, let's say he moves 2, so the agent would get there much faster. Therefore, because m, your heuristic, h, has to satisfy less than the optimal, is it less than m over, let's say, moves Vmax equals 2? And the answer is no. Therefore, this is not admissible. Okay, so for question 3, state and justify a non-trivial admissible heuristic for this problem, which is not the Manhattan distance to the exit. So there's a few answers to this question, and we're going to cover a few of them. So one of them would be the number of turns to face the goal. So why would this be admissible? So let's say my goal is here, and my agent is facing this way. No matter what, to move up, since you can only move in the direction that you're facing, the agent will have to at some point look towards the goal. Therefore, this is a relaxation. Okay, so let's do another heuristic. So one heuristic is similar to number 2, the Manhattan distance, but let's take into account speed. So usually what we do is, let me erase this. So normally we do Manhattan distance because for Manhattan, we're allowed to move distance 1. So maybe we can generalize this. What if we do Manhattan, but now we make the number of moves some variable v. So really, we can come up with heuristic that is going to be Manhattan divided by your max velocity. So another way to put this is that this would be Manhattan is your distance, and v, which is in, let's say, meters, and v max is meters per second. So that would give you seconds. So you're trying to underestimate the time. Okay. And now I'll briefly touch on a third possible heuristic, although there could be many, many more. So we can improve upon number 2 by accounting for acceleration and deacceleration. So because it takes time to go from 0 to v max and back down to 0, the goal, we can actually improve upon 2. So 3 would be an improved version, where it would be Manhattan divided by some v, possibly average, or something like that. And I encourage you to try to come up with other heuristics. Okay, so let's move on to number 4. If we used an inadmissible heuristic in A-star graph search, would the search be complete? Would it be optimal? Okay, so in graph search, in general, if it's bounded, as in if there's a finite number of states, the costs and the heuristics only tell you which nodes to expand first. But eventually you'll go and you'll expand all of them. Therefore, it would be complete. Because graph search, so let me repeat it. For finite states, it'll always visit everyone. Now, next question is, would it be optimal? So if we look at, remember from the mini lesson before, so A-star graph requires consistency. Now, we have all the space of all admissible, and consistent is always admissible also. So if we're not inadmissible, then we're also definitely not consistent. So we are not optimal. The answer is no. Okay, so for number 5, if we used an admissible heuristic in A-star graph search, is it guaranteed to return an optimal solution? And the answer, as we talked about above, this is also no, because we require consistency. So what if the heuristic was consistent? And then A-star graph search will be optimal. Yes. Okay, so moving on to number 6. Give a general advantage that an inadmissible heuristic might have over an admissible one. So in general, we're going to think about two different metrics when we're doing our search. So one of them that we've been talking about a lot is optimality. Does my search algorithm give me the best solution? But when you're also in the real world, you also have speed and time. For example, if you'll find the optimal solution, but it'll take you 2 days, maybe you'd rather find something suboptimal in 6 seconds. So an inadmissible heuristic could help you get speed. Now, why might that be? It might be easy to compute. So let's say we have this Pac-Man grid, and Pac-Man starts here and wants to get to the star. There can be a complex curve walls blocking it from getting to the goal star. So one approach would be to do uniform cost search and expand all the nodes, and you'd find the star. Or you could come up with an H that helps you find a path there, but it might be slower. Actually, sorry, it might be suboptimal, but it would speed up your search and you would find the goal faster. So if this heuristic is inadmissible but helps you get more speed, it might be advantageous. Okay, so now let's move on to constraint satisfaction problem. So here's the problem. So we have, or take a second to read it, and then I'll go over it. Okay, so we have some classes, class 1, 2, 3, 4, 5, and they're scheduled for different times. We also have different professors, A, B, and C, and each of them is qualified to teach only some of these classes. So our ultimate goal will be, can we find a schedule such that all the classes have a professor to teach them, because you need a professor to teach the class, but so that there's no constraints. So some of the constraints might be we need to make sure that the teacher is actually qualified to teach the class, and we also need to make sure that they're not set to teach 2 classes that occur at the same time, because the teacher can't be in 2 places at once. So first, for CSPs, we have 3 things that we need to define. We need to define the variables, the domains, and the constraints. So this is what problem 1 is going to ask us to do. And in general, this is what all CSPs require you to do. Okay, so for the variables, we have the classes. So we'll call them C1, C2, C3, C4, and C5. Okay, now we're going to talk about the domains. So for the domains, what can C1 take on? So these are often unary constraints. They're constrained only on one variable. So for class 1, the domain is only those professors that are classified are allowed to teach it. So the only professors that can teach class 1 are going to be A and C. In class 2, the only professors who are qualified to teach it are Professor A. For class 3, the only professors qualified to teach it are B and C. For class 4, the only professors able to teach that are also B and C. And for class 5, the only teachers qualified are A and B. Okay, so that's our domain. So now, what are our constraints? So we already took care of the unary constraints, which are the domains. So a different approach would have been, I could have had each class been A, B, and C. For all of them, ABC professors, all the professors can teach them, and then added constraints on that only involved one professor. But in general, what we do to simplify things is that the domain is only the values that the variables can take on. Okay, so now for constraints, we want to make sure that all the classes that occur at the same time don't have the same professor. So for example, let's look at class 1 and class 2. So they overlap for 30 minutes. Therefore, whoever teaches class 1 cannot also teach class 2 because they overlap. And we can continue going through all of these. Now looking at class 2 and class 3, they also overlap for 30 minutes, so they can also not be equal. Also, we have class 2 and class 4 also overlap for 30 minutes, so those cannot be equal. And we also have class 3 and class 4, which are actually at the exactly same time, so they can also not be equal. And we look at class 5, and class 5 is fine. It has no conflicts. So these are our variables, domains, and our constraints. So now problem 2 asks us, can we draw the graph that's associated with this? So first what you do is you draw all your variables as nodes. So class 1, class 2, class 3, class 4, and class 5. Oh. And class 5. Okay. So now what we do is we draw all of our constraints as edges in the graph. So C1 and C2 are connected by a constraint. C2 and C3 are connected by a constraint. C2 and C4 are connected by a constraint. And C3 and C4 are connected by a constraint. So this is our CSP problem.